Hello geometry students, welcome to our 7.4 notes, parallel lines and proportional parts. So let's take a look at these first two theorems, and what we're going to do is, instead of writing out a big long theorem, we're just going to state the theorem in terms of this diagram. So the first one is called the triangle proportionality theorem, and here's what the theorem says. It says that if we have a segment that touches two sides of a triangle and is parallel to the third side. So look at segment BE. It's touching two sides of the triangle and it's parallel to the third side. So that's a hypothesis of this theorem, that if we have a segment BE that is parallel to a side of a triangle, the conclusion is that this segment is going to cut the two sides that it touches into segments that are proportional, or cut it into proportional pieces. So in other words, the ratio of AB to BC is going to be equal to the ratio of AE to ED. So let's go ahead and write that proportion, that the measure AB to BC is equal to the ratio of AE to ED. All right, so again, if we have a segment that touches two sides of a triangle and it's parallel to the third side, then that parallel segment cuts the other two sides of the triangle into segments that are proportional. So AB to BC is equal to AE to ED. All right, now the converse is also true. So we're going to take this hypothesis and this conclusion and just switch them. Okay, so the converse would say, if we have a segment that is cutting the sides proportionally, in other words, we have the segment EB that's cutting the sides so that AB to BC is equal to AE to ED, if that's true, then our conclusion is going to be what the hypothesis was over here. The conclusion is going to be that segment BE is parallel to the third side of the triangle. Oops, I forgot my parallel symbol. There we go. Parallel to the third side of the triangle. So let's use these theorems to solve some problems. So this first example says find the value of x. So what we need to notice in the diagram here is these two little arrows that shows that this segment is parallel to this segment. So if we have a side that's of a segment that's parallel to a side of a triangle, it's going to be cutting the other two sides proportionally. So in other words, I can write the ratio of x to 2.5 and set that equal to the ratio of 7.5 to 3. All right, so that's a proportion that we can solve. Well, if we cross multiply, we're going to get 3x equals 7.5 times 2.5 is 18.75. We'll divide both sides by 3, and x turns out to be 6.25. Now, the direction said find the value of x, and we've done that, so this problem is finished. Okay, so let's take a look at the next example that says find the value of x that guarantees that segment DE is parallel to GH. Well, that's going to be true, and let me turn that around and say GH is parallel to DE if GH is cutting these sides of the triangle proportionally. So let's find the value of x that would make that happen. So let's take the ratio of 4 to x and set that equal to 3 over 9. And again, as always, there are many different ways you could write this proportion. I could have said x over 4 equals 9 over 3. That would have been fine also. So let's go ahead and solve this proportion. We'll cross multiply, and 4 times 9 is 36. And we'll set that equal to 3x. Divide both sides by 3, and I'm going to turn that around as well and say x is equal to 12. So at that point we're done, because the direction said find the value of x. It would guarantee that these segments are parallel. The next thing we're going to look at is something that will sound very familiar to you. We're going to define the midsegment of a triangle. Definition says the following: a segment is a midsegment of a triangle if and only if its endpoints are midpoints of the two sides of the triangle. The reason why this sounds very familiar to you is because in the last unit we studied the midsegment of a trapezoid. Remember, the midsegment of a trapezoid was a segment whose endpoints were midpoints of the legs. Well, so the same thing is true here. A midsegment is going to be a segment whose endpoints are midpoints. So for example, I'm going to guesstimate where the midpoint is of this side of the triangle and guesstimate a midpoint here. Okay, the segment that connects those two midpoints is called a midsegment. Now, a triangle isn't going to have one midsegment, it's going to have another one. It's going to have two more midsegments, because if I find the midsegment of the third side, let me put tick marks to guarantee that that's or to indicate that that's a midsegment, then this blue segment is also a midsegment, and this green segment is also a midsegment. All three of those segments, if you look at their endpoints, they are midpoints of a side of the triangle. Okay, so now we're going to learn what's called the triangle midsegment theorem, which says the following. A midsegment of a triangle is parallel to one side of the triangle, and its length is 1/2 the length of that side. Again, this is going to sound familiar to you, because when we talked about the midsegment of a trapezoid, remember the midsegment of the trapezoid was parallel to the bases, and then its measure was the average of the two bases. Well, you could almost theoretically think of this triangle as a trapezoid where one base has a length of 0. So if I average 0 and this together, add 0 to this, divide by 2, we would get half of whatever BC is, and that's the measure of segment DE. So in terms of this diagram, if DE is a midsegment of triangle ABC, so if segment DE is a midsegment, okay, then that implies two things. Number one, that DE is parallel to one side of the triangle, so DE would be parallel to BC, and the measure DE is equal to 1/2 the measure of BC. So let's use that midsegment theorem a triangle midsegment theorem to find these measures. So the first thing we're going to find is we're going to find the measure of DE. So I just want you to notice that this point D is a midpoint, this point E is a midpoint. So that means that this segment is a midsegment, and we know that the midsegment is parallel to a side of the triangle, and it is also half the length. Okay, so if we know that segment AC measures 15, we know that DE, the midsegment that it's parallel to, is going to be half of that. So DE is 7.5. And then let's find the measure AB. Let's find AB. Well, to find AB, I want you to take a look at this segment. Again, E is a midpoint and F is a midpoint. So therefore, we know that segment FE is a midsegment, and it's going to be parallel to a side of the triangle, and it's going to be half its measure. So if segment FE is 9.2, segment AB would be double that, so that would be 18.4. And then the last thing we're going to find is the measure of angle FED. So let me mark that angle, which would be right here. Well, I want you to recall from the last example that these blue segments are parallel, aren't they? Remember, a midsegment is parallel to a side of the triangle. So we have some parallel lines in a transversal. So this 82-degree angle and the angle that we're looking for are on alternating sides of that transversal and on the interior of the two parallel lines, so that's a pair of congruent alternate interior angles. So if this angle is 82 degrees, then angle FED that we're looking for is also 82 degrees. So there are a couple of corollaries to the triangle midsegment theorem, and the first one looks like this. It's called the proportional parts of parallel lines. So if you'll notice, we have three lines here that are parallel. We know they're parallel because of the way they're marked. And these three parallel lines are intersecting two transversals. Okay, so what the proportional parts of parallel lines corollary tells us is that if we have three parallel lines, so that would be AE, that's parallel to BF, which is parallel to CG. Okay, so we have three lines that are parallel, and those parallel lines are intersecting two transversals. Let me just highlight the transversals. So the parallel lines are intersecting this yellow transversal and intersecting this blue transversal. The conclusion of this corollary says that these parallel lines are cutting the transversals proportionally. So in other words, the ratio of AB, this piece to this piece, so AB to BC, Proportional, remember, means equal ratios. So the ratio of AB to BC is equal to the ratio of the parts of the blue transversal. So that would be EF to FG. So EF to FG, okay? In other words, another way we can state that is 3 or more parallel lines, okay, will cut transversals. How will they cut them? Cut them proportionally. All right. Okay, so let's take a look at this example. It says find the ocean frontage of lot A. So we have these lots that, I wish I lived there, that come right up to the ocean. And so what I want you to notice is kind of tiny, but notice these little markings that show that these lines are parallel. So if those lines are parallel, then we have some parallel lines that are intersecting some transversals. So here's one transversal I'm going to highlight yellow, and another transversal that I'm going to highlight blue. So what this proportional parts of parallel lines corollary tells us is that these parallel lines are cutting these transversals proportionally. So let's go ahead and indicate what we're trying to find here. We're trying to find the ocean frontage for lot A. So let's call that X. And so since these transversals are being cut proportionally, we can write a proportion. We can say that X to 60, so let me go ahead and start that, X to 60 is going to be equal to the ratio of the parts of the blue transversal. So that would be 48 to 52, or I'm sorry, 58 to 42. So 58 to 42. Okay, so cross multiplying, we would get 42x is equal to 3,480. If we were to divide both sides by 42, and I recommend that you get a calculator for that, we're going to go ahead and round off our answer. The answer is technically about 82.857, but let's just go ahead and round that to the nearest foot. So we'll say that this ocean frontage for lot A is about 83 feet. And now let's look at another corollary that follows from the previous corollary and the triangle midsegment theorem. It's the congruent parts of parallel lines corollary, which says if 3 or more parallel lines cut off congruent segments on one transversal, then they cut off congruent segments on every transversal. So you can see we have 3 parallel lines. You can tell by the markings, okay? Now, these 3 parallel lines are cutting off congruent segments on one transversal. So let me highlight that transversal yellow. So the 3 parallel lines are cutting the yellow transversal into congruent parts. So that means it's going to cut every transversal into congruent parts. So this blue transversal is being cut into two congruent parts also. So let's go ahead and state the theorem in terms of this diagram. So the hypothesis says we have 3 pairs of parallel lines. So if line AE is parallel to line BF, which is parallel to line CG, okay? But don't stop there for the hypothesis. There's also the condition that these parallel lines are cutting one transversal into congruent pieces. So we also have to assume that segment AB is congruent to BC. So if all of that is true, then that's going to imply, then we can conclude that the blue segment is being cut into congruent pieces as well. So in other words, EF is congruent to FG. Now, make sure that you're understanding what this really says. It's saying that if this yellow transversal is cut into pieces that are congruent to each other, then this blue transversal will be cut into pieces that are congruent to each other. What it's not saying necessarily is that AB would be congruent to EF and BC would be congruent to FG, okay? What it's saying is that if the yellow transversal is cut into these 2 pieces that are congruent to each other, then this blue transversal will be cut into 2 pieces that are congruent to each other. So let's take a look at an example. Notice we have 1, 2, 3 parallel lines that are cutting 2 transversals, and you also need to notice closely here that we have these tick marks. So what that means is that the 3 parallel lines are cutting this yellow transversal into pieces that are congruent to each other. So what that means is that these pieces are congruent to each other as well. So if we're asked to find X and Y, we can use the corollary to say, all right, if these two pieces are congruent to each other, then these two pieces, let me go ahead and highlight that transversal as well, then this is being, the blue transversal is being to cut into pieces that are congruent. So in other words, we can say that 6x minus 5 is equal to 4x plus 3. Okay, and so let's go ahead and subtract 4x from both sides, and we get 2x minus 5 equals 3. I'm going to add 5 to both sides. We get 2x equals 8, so x is equal to 2. Okay, and then we were also asked to find y. Well, we were given, the tick marks tell us that these two segments are congruent, which means these measures are equal. So to find y, we can set 3y plus 8 equal to 5y minus 7. And then I just want 1y on one side, so I'm going to subtract a 3y from both sides. And we'll get that 8 equals 2y minus 7. Then we'll add 7 to both sides and get that 2y is equal to 15. We're going to divide both sides by 2. So y is 15 halves, or you could call that 7½ if you like. Okay, so you can go ahead and mark this homework out. We're actually going to do a worksheet in class next time, and so I will see you in class, and if you have any questions on the notes, be sure and ask me then.